Now, the way that these different elements react and the reason that they react really has mostly to do with their electrons. Electrons are the #1 determining factor when we look at whether an element will or won't react and then how it will chemically react. So if we think back to the makeup of an atom, we know that there's a nucleus, which is a very, very small area at the center, and the rest of the space around the atom has some electrons. Remember too that the electrons are moving extremely quickly and they're very, very hard. In fact, they're nearly impossible to pin down. We never know quite where they are, and yet where they are is what tells us how this atom is going to react. So since we can't pin down the electrons and we can't say exactly where they are, instead we do our best to describe the area where you're likely to find them. The area where you're likely to find them is described in 3 different terms in chemistry. The first is we tend to describe the shell that you can find the electrons in. We'll look at what that means along with the terms subshell and orbitals. These 3 terms are essentially an address that helps you find or have your best attempt at finding where an electron would be in an atom. So let's go one at a time and look at shells, subshells, and orbitals. What the shell indicates in an atom is really how far away from the nucleus you're likely to find a particular electron. Shells are numbered 1, 2, 3, and so on, and if you think of the nucleus as being in the center of the atom, shell number 1 would be the shell that's closest to it. So remember, even though I'm going to show these as circles, atoms, like everything in life, are 3-dimensional, so this really is more of a sphere. It's a lot like the shell around an onion. So shell number 1 is closest to the nucleus. Shell number 2 would be a little bit far away from the nucleus, and that would continue through shell number 3 and so on. Now, not only do these shells describe how far away from a nucleus an electron is likely to be found, they also essentially describe the size of that atom, and they correspond to, believe it or not, the periods on the periodic table. So when we say shell number 1, not only do we mean an area pretty close to the center of the nucleus, we also mean the electrons that come from the elements in the first period of the periodic table, hydrogen and helium. Shell number 2 would have the electrons that are part of lithium and beryllium and everything else in period number 2. Same with shell number 3, corresponds with electrons from the elements in period 3 of the periodic table. And this continues all the way down the periodic table. Period 4 corresponds to shell number 4, period 5 corresponds to shell number 5, and you can continue going through shell number 7. Because shell just tells us how far away the electrons are spending their time from the nucleus, we really do need more of a description to be helpful. And when we look at describing in more detail where the electrons are going to be found, we get into some really interesting areas of chemistry that are a little strange if you haven't seen them before. So let's talk about subshells and orbitals, and remember, if you haven't felt like chemistry was a different language already, this is probably where it will sound pretty strange. A subshell and an orbital as well is just a description of the area within a shell where an electron is likely to be found. So if you go from the nucleus out to shell number 1's radius and you start looking around for electrons, knowing the subshell and the orbital it's in will give you a better description of where it's likely to be found. The first type of subshell that you can possibly have is called an S-type subshell. An S-type subshell is essentially just a simple sphere. That sphere is the area around the neutron where the electron's likely to be found. And it's a pretty simple area, so we actually say it just has one orbital in there, or one orbital of space where the electron can be found. The P-type subshell is the next type of subshell. If you have a P-type subshell, you have an area that's a lot more complicated to think about. Instead of having a simple sphere shape, a P-type subshell is actually a propeller or a two-lobed type of shape, and each of those lobes represents an area where you could find an electron. The reason that the P-type subshell is more complex is that not only do we have a lobe going above and a lobe going below the nucleus, because it's a three-dimensional atom, we actually have this happening in 3 dimensions. So if you think of this particular subshell as being an up-down p subshell, you'll also have one going forward and backwards and one going left and right. So it covers all 3 dimensions. And remember, these are all overlapped on top of each other. So even though they're strangely shaped, remember it's just a way of describing an area where you're most likely to find electrons. The S subshell is a spherical area. The P subshell is a 2-lobed area, and you've got those lobes going in different directions. Now, if you think the P-type subshell is a little weird, I can tell you they only get worse from there. And while they're interesting, we don't really need to be able to see them in order to make this information useful in day-to-day chemistry. So while the S subshell has 1 orbital, the P has 3 orbitals, I'm not going to show you pictures of any larger subshells because they do get more complicated. The D-type subshell, for instance, has 5 orbitals, so 5 different areas where you can actually find those electrons. And if you were to have a very large atom where you would encounter an F-type subshell, that would actually have 7 different areas. So you can see that it does start to get complicated. But here's what I want you to remember about this. Even if you can't picture the shapes, that's okay. The main thing that this tells us is where to find the electrons, and even more importantly is how many electrons there are. Now, how do we know how many electrons can fit in these spaces? That's where the orbitals come in. So an S-type subshell, yes, it's a spherical shape, but because we know it has 1 orbital, I can tell you that every single orbital is capable of holding up to 2 electrons. So if you are looking at an S-type subshell, you might find 1 electron in there, you might find 2 electrons in there, but I guarantee you will not find any more than that. So an S subshell can hold 2 electrons, a P-type subshell can hold 6 electrons, and if you look, you'll start to notice a pattern. Because there's 2 electrons in each of those orbitals, we know that the D subshell with 5 orbitals is 10 electrons. So we can have up to 10 electrons in the D subshell, and we can have up to 14 electrons in the F subshell. So really, if you want to boil this down to the simplest way to think about it, think about this information as a way of saying, now that I know there are electrons in the atom, where are they? Well, your shell tells you how far away from the nucleus to look for them, and your subshell tells you how many electrons to look for there. The other nice thing about this is that the subshell corresponds to the periodic table. And this isn't going to be quite as helpful until we actually start to put it to work. But if you're dealing with an atom that has S subshells, which we'll see that all atoms do, the S subshell actually corresponds to the electrons that are usually found in the first 2 groups of the periodic table. So if you're doing electron configurations for any of the elements in group 1 or group 2, the very last subshell you'll find yourself working with is S. Now, if you find yourself working with the P subshell, I can guarantee that at the very least you're dealing with an electron from what we call the P block, or the P area of the periodic table. The D area is the transition metals, and the F area is the lanthanide-actinide series, which is down on the bottom of the periodic table. That lanthanide-actinide series is not going to be especially relevant for us in this class, so often you'll see me leaving it off of the screen. That's just to simplify things, but it follows all the same rules that we're going over for the other elements on the periodic table. Okay, so now that we've done all that, here's how we put it together. Or as you're probably thinking, here's how I'm actually going to ask you about this on an exam. We have to put all this information together to describe where we find electrons. And we put this all together into what's called an electron or an electronic configuration. It's how the electrons are configured inside of an atom. This is important because, as we're going to be seeing throughout the quarter, where the electrons are tells us, well, are those electrons available to do a chemical reaction? So let's look at doing a couple electron configurations. We're going to write the electron configuration out for separate elements. For each one, I'll give it to you, I'll show you how to do it, and then we'll do a few more for practice. Let's start out with something simple. I've got the periodic table down on the bottom of the screen. I've labeled your period numbers, which of course correspond to shell number. And there's your subshells so that you can start to see the pattern that'll make these easier and faster to do. Let's write the electronic configuration for a very simple element. Let's write the electronic configuration for an atom of hydrogen. Now hydrogen, capital H, is your first element on the periodic table. So when we go to describe where the electrons are, we're always going to follow in the same order. The way we're going to do that is by first writing which shell number my electrons are in. Well, we're starting out with a very small atom, and the way we're going to start all our electron configurations is where you might guess. We're going to start out with shell number 1. So I write a 1 to indicate that I'm currently dealing with electrons in the first shell, meaning closest to the nucleus, and then where that first electron goes depends on which shell number I'm in. Well, I'm in shell number 1, and the simplest subshell I can possibly have is S. If I have hydrogen, you'll remember that we said for neutral elements, the number of protons is equal to the number of electrons. So hydrogen, atomic number 1, must have 1 electron in it. That 1 electron is going to be found in the 1s subshell. So to indicate that there's just 1 electron, I'm going to write a superscript or an exponent 1. 1s1 is the electronic configuration for hydrogen. It tells you the electrons in hydrogen are in the first shell and they're in the spherical S-type subshell. If I wanted to do helium, helium is going to have 2 electrons, but it'll start the same way. Helium, or He, has 2 electrons. Well, if I think about it, all my first electrons go into the first shell, and then there's going to be at least 1 in the S-type subshell. But remember, how many electrons fit in the S subshell? If you go back a minute, you'll see that it was 2 electrons. So I have room for both of those electrons, so I'll write a 2. That means there are 2 electrons in my first shell in the S-type subshell. You might also remember that that's the maximum amount that an that an S subshell can hold of electrons. So if I move from helium to the next largest element, which is lithium, I am going to have to start a new subshell. Now the rule for this is every time you increase the shell number, you get to use 1 more subshell. So if you're in shell number 1, you can use 1s subshell. If you're in shell number 2, you can start a brand new S subshell, and you can also use a P subshell. If you're in shell number 3, you can start a brand new S subshell, and then a brand new P subshell, and then a brand new D subshell. So it's a nice regular repeating pattern. So let's try lithium. Lithium, or Li, is atomic number 3 on the periodic table. So as I go to do lithium, I need to find out where the electrons are if I have 3 electrons. Well, the first 2 electrons are still going to be in that innermost shell. Atoms are a lot like onions. You start by building the small inner shell, and then you can build the larger shells from there. So my first 2 electrons are going to be in 1s, and there's 2 of them. Now I've run out of room in the S subshell, so I get to start my second shell. That's going to have an S subshell to start with, and there'll be 1 electron in it. Okay? Notice a couple things. I'm in the second period, and so not surprisingly, my lithium goes through the 2 shell number. Also, lithium is in that S block, or the green area on the left side of the periodic table, and it's in the first group, so that's why it ends with S1. If I were to go all the way to the other side of period 2, let's do the electron configuration for neon. Neon, or Ne, because it's atomic number 10, has a total of 10 electrons. And I'm going to have to fill these up in the same order. So my first 2 electrons go into the first shell in the S subshell. My next electrons go into 2s. S can always fit 2. So now I've taken care of a total of 4 electrons. And I still need 6 more electrons. So that's where my 2p subshell is going to come in. And I need 6 of those. So that's the electron configuration for neon. When you're dealing with these, one of the things you'll notice is they're really repetitive. So it's not so much about having to rethink these every time, it's just remembering the general pattern. Now I'm going to write down the pattern, and I'm also going to post a link on our webpage so that you can look at a complete periodic table with all these electronic configurations filled in. And I think you'll notice that the pattern is very regular, very repeating. Any element I'm trying to come up with the electron configuration for, I basically write the following information and I stop when I have all the electrons I need. So as we see, for any element, it's always going to start out the same way. I always start with 1 and I have to go into my S subshell. I can have 2 electrons there. That fills up my S subshell, which fills up my whole shell. So now I have the second shell. That can have an S subshell first, which has 2 in it, and then it can also have a P subshell, which can fit 6. At that point, for 2, I have 2S and 2P. It's filled. I have to go to my third shell. This is where I can have 3 start with S. There's 2 of those. Now I can have 3P, and there's 6 of those. And here's where it gets a little bit out of order. At this point, I would expect, since I'm in the third shell, that I have 3S, 3P, and now I can have 3D. But if you look carefully at the periodic table, you'll notice that the next thing I'm going to run into is not, in fact, 3D. I'm actually going to be in the fourth shell and doing 4S. And so this is where things go a little bit out of order, and it can really help to have the periodic table, because this exception isn't so much an exception as a rule. After 3PS, we can fill up 4S2. So as we go to 4S2, that moves us along the periodic table, and from there, I'll just jump up here a little bit, now we can finish that D. So notice this transition metal area of D's is called the N-1 area. In other words, it's always one number less than what you're working with. Here's 4S2, so we're going to have 3D10 before we continue again with 4P6. And that's going to continue the rest of the way down the periodic table. Alright, so test yourself. I'm now going to start writing the electron configuration for something really, really big with a lot of electrons, dozens and dozens of electrons. See if you can say what I'm supposed to write next. Okay, I always start with 1s2, 2s2, 2p6, 3s2, 3p6, there's the exception, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Are you done yet? Want to keep going? Okay. I better go to the next line. 6s2, and here we run into the lanthanide-actinide series. At this point, you would have to drop down to the N-2 F subshell bracket, which is a lot. And we're really not going to work with elements that far down the periodic table. So as long as you can get this far on your electron configuration, I will be completely happy. So again, the order is always 1s2, 2s2, 2p6, 3s2, and so on. And really, you just write this out and stop when you have all the electrons you need. The only other thing we're going to add to these electronic configurations right now is a way to give some visual information to them, because they're essentially just a long sentence of numbers and letters that show us where to find the electrons. We can add to the electron configuration what's called a line diagram. And a line diagram is really a set of visual symbols that we add that'll help us know what's actually going on. In this configuration with added symbols, the symbols are really just orbitals and electrons. Orbitals are depicted as lines, and electrons get depicted as arrows. So let me give you an example, and this will be good practice. I'm going to write the electron configuration for oxygen. When you do that, make sure you give yourself lots of space because we're going to add some extra information to it. If you want, go ahead and pause the video and see if you can figure out the electron configuration for oxygen. Alright, so the electron configuration for oxygen is 1s2, 2s2, notice I'm giving myself some extra space, and it goes as far as 2p4. Again, I know that because I just start working my way up, and in this case I only needed 4 of those p subshell spots because I needed a total of 8 electrons, and here I have 8 electrons. Now here's how I take this electron configuration and add a line diagram. I'm going to represent all orbitals as lines. If you think back, we learned before that s subshells have 1 orbital, p subshells have 3 orbitals, d subshells have 5 orbitals, and f subshells have 7 orbitals. So I'm going to add a line above my 1s2, just one line to represent that 1 orbital. Above my 2s2, well again, it's an s subshell, so I'm adding 1 line. Now I have a p subshell. P subshells have 3 orbitals, so I'm going to add 3 lines. Now, my last part is to add the electrons. When we add electrons, they're represented by arrows, and I'm going to add as many as my superscript or my exponent tells me to. For this first orbital, I have 2 electrons, so I'm going to draw an up arrow to represent 1 and a down arrow to represent 2. We always draw the up arrow first, followed by the down arrow. Another thing you can do when you write these, if you want to go quicker, is it's okay to use a half arrow. So in my second shell, it's still an S. There's still 2 electrons. So there's an up arrow, kind of a fast version of it, and there's a down arrow. Now when I get to this 2p4, I have a little more to consider. I have 4 arrows, 4 electrons, and when I put them in, I want to make sure they go in the right order. We always fill in each orbital with 1 up arrow before we add any pairing down arrows. So in this case, I need to add 4 arrows. I'm going to add 1, 2, 3, and now I can go back to do 4. This is the electron configuration and the electron line diagram added to it. What it tells us, you'll probably notice, is basically how reactive that element's going to be. What we're going to see in later chapters is the fact that there are holes in this line diagram. If you look there, you can see 2 unpaired arrows, indicates that this atom is probably going to want to bond with something else. And in fact, this is why oxygen in its elemental state is usually O2. It essentially had to find a partner to fill in these unpaired arrows. Let's do one more for practice. Let's do, how about chlorine? Chlorine is number 17 on your periodic table. Again, if you'd like, you can pause this video and go ahead and do the electron configuration and then add the line diagram for chlorine. Okay, so first I'm going to do my line diagram. I need 17 electrons for chlorine. 1s2, 2s2, 2p6 because I'm filling that up, 3s2, and now to complete my 17 electrons, I need 3p with 5 electrons in it. Now I'm going to go in and add lines for each orbital. S orbitals always get 1 line, so there's an S, here's another S, and then p orbitals get 3 lines. 1, 2, 3, 1, 2, 3. Now I'm going to fill in the arrows. 1s2, I go up and down. 2s2, I go up and down. 2p6, even though it won't make a difference in your final answer, I go up, 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 down, down, down. 3s2 and 3p5. Here's where it will make a difference. Up, 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 and then here's 4, 5, and I stop. Again, notice there is a missing arrow here from the chlorine's electron configuration line diagram, And that's why chlorine is another one of those elements that we rarely see truly as a single atom in nature. Okay, one more thing and then you're done. You probably want a shortcut for all this, and that's okay. Notice that the electron configurations get really long and they're very repetitive. So here's a shortcut you can use when you're doing electron configurations, and you can use it even when you're doing line diagrams. Instead of writing out all of the possible 1s2, 2s2, 2p3, the entire thing, anything that's been already completed, any shell that's already complete, can be substituted with the symbol for the closest noble gas. So let's do chlorine since we just did it. On our periodic table, here's chlorine. And we had just filled it out and it kind of took a while. But what I can do is go back to the noble gas that precedes that group. What that means is if I move across the period, before I got to chlorine, the last noble gas was neon. So neon was the noble gas before chlorine. So instead of writing all of the details that go into the electron configuration of chlorine, I can substitute in all of the electron configuration of neon just by putting in neon in brackets. That means 1s2, 2s2, 2p6, which is the electron configuration for neon. I'm only allowed to do that for the noble gas part. Now I have to fill in the rest. Neon, because it's in the second row and it finished with 2p6, means now I have to pick up on the third period. So 3s2, 3p5. Okay, so there's my up, down, and here's my up, 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 down, down. That is also a completely acceptable way to do the electron configuration and the line diagram for neon, and I encourage you to use it. It's a lot easier, it saves time, and to be honest, it's easier for me to grade. Now, this is a very, very tricky area of chemistry, and I don't want you to get frustrated with it. So please look at the link online so you can see the regular repeating pattern that shows up for electron configurations. Make sure you read our objectives so you know exactly how I'll ask you about these. And of course, don't hesitate to call me or email me anytime if I can help you with these.